Okay, so we're going to be talking about logarithmic functions, and the last class we talked about exponential functions. An exponential function was f of x equals some base to the x power. So what a logarithmic is it's the inverse of an exponential. So let's talk about inverses. If we were to find the inverse, we would want to switch x and y, right? So if I make that y equals b to the x, then I could switch my x and y. Well, mathematicians were like, well, how do I solve for y from here? How do I find something that will give me the exponent? And the function that does that gives me the exponent as an answer is called a logarithm. A logarithm finds the exponent. So the answer to a logarithm is always the exponent. So the way it would work is that exponent, the y, is the answer to the logarithm. Now we have to tell the logarithm what base we were using, so that's a little subscript there, and we have to tell it what we want to get from that base to that exponent. So we have to give it that x value. So again, this is the exponent. The answer is always the exponent. This subscript is the base. And we call this the argument. It's what we're trying to get as far as b to what power gives me that answer. So let's just kind of do a little bit of rewriting, thinking about how these two are related. So what we're going to do is we're going to take a logarithm and we're going to rewrite it as an exponential. We're going to break it down into what it means. This base to this exponent gives me that answer. So if I had 2 equals log base 5 of x, what that means is that this is the base, the 2 is the exponent that gives me that answer. So what about log base b of 64 equals 3? I wrote it a little backwards, but it means the same thing. So the base is b, the exponent is the answer of a logarithm, equals 64. Let's do one more. And I challenge you to try it first. Base, exponent, answer. Base, exponent, answer. Well, can I work the other way? If I was given an exponential, can I write in logarithmic form? So if I was given 12 squared equals x, how would that look as a logarithm? Well, the base is a subscript written beside the logarithm. The argument is what we're trying to get to, and the answer to a logarithm is always the exponent. So the base, exponent, argument. The argument is the answer from the exponential. So b cubed equals 8 would be log base b of 8 equals 3. Log base argument equals exponent. Well, now that we've practiced what a logarithm means, the next thing we're going to do is actually evaluate it. That means we're going to actually solve it. Okay, so let me show you what I mean by that. Okay, so we're going to evaluate. So if I had log base 10 of 100 equals blank. Okay, so we're trying to figure out what the answer is to the logarithm. The answer of a logarithm is always the exponent. But it's the exponent for what? So what we're trying to find here is the base is 10. This is the exponent, and we're trying to get to 100. So what fills that box in? 10 to what exponent gives me 100? Well, that would be a 2. Let's try log base 5 of 1 over 125. Ooh, a fraction. So we're trying to find the exponent that would give us a fraction answer. So 5 to what exponent would give me 1 over 125? Well, if you don't remember your exponent rules, I invite you to try some things in the calculator. So what could I try? Well, let's see. I know 5 cubed gives me 125. What about 5 to the, what if I make the exponent a fraction? Would that work? Well, is that the same as 1 over 125? Ooh, not even close. So how about 5 to the negative 3? That does it. A negative 3 moves it to the denominator, and so now we have a fraction. So to get a fraction, the exponent has to be negative. What about log base 36 of 6? How would I get something smaller? So 36 to some exponent is going to give me 6 as an answer. So again, we're 36 to some exponent. So 36 squared. No. 36. How would I just get a 6 back? To the 1/2. Oh, I remember that something about when an exponent is a fraction, like 1/2, gives me a square root. And it does. So 36 to the 1/2 gives me 6. Alright, so that's something to remember, that a square root can be a 1/2. That would mean a cube root is 1/3. A fourth root would be 1/4. Those are things we want to make sure we remember. Oh, these are getting a little close together. I'm going to scoot down a little bit. Log base 3 of, the 7th root of 3. So let's think about what that's trying to say. That is asking, base is 3. 3 to what exponent would give me the 7th root of 3? Thinking back on what we just did there. 1/2 was a square root. So how would I get a 7th root? It would have to be 1/7 as an exponent. Now we're going to get into some fun ones. I need to switch pages. So if you need to pause, pause. So we're still evaluating. We're still trying to find the exponent. So base, exponent, argument. Base, exponent gives me the argument. This is a nice one. It's just 1. 7 to the first power gives me 7. Let's try another one. Log base 5 of 1 equals what? So 5 to what exponent gives me 1? Think back about when we did the exponential graphs. 5 to what exponent gives me 1? That'd have to be a 0. Anything to the 0 power gives me 1. This one looks tricky. Base is 4. To what exponent gives me the argument? It's not that tricky. It's just a 5. Now remember, we also said that logarithms and exponentials were inverses. They undid each other. So it's almost like that whole thing kind of canceled each other out and we were left with that exponent. Now using that rule, if I switched them around and had an 6 to the power of a log, what do you think is going to happen there? So kind of here they canceled out and left me with the 5. Here, this part's going to kind of cancel out and leave me with just the 9. So logarithms have some nifty properties. Now we want to talk about a couple more things. One thing is going to be the graph. So I want you to remember that they are inverses of each other. So if I wanted to graph I can think of the fact that this is the inverse of two to the x. They have the same base. These are actually going to be inverses of each other. So what I can do is I know how to make a table and graph 2 to the x. And then I'm going to use that rule about switching x and y to graph its inverse. So let's make a table. And we're going to make a table for 2 to the x. Okay, so that was x, y. Okay, so let's just go from -2 to 2. That's good enough. And so 2 to the 0 power was 1. 2 to the first power is 2. 2 squared is 4. And when I went backwards, I got fractions. And so I'm going to graph that one in one color, and then we'll graph the logarithm in a different color. So I'll do red for this one. Okay. So let's see. 1, 2, 3, 4. 1, 2, and so forth. Okay. So so -2 went to a fourth, half, 0, 1, 2, and then the next one will be an 8. Remember that it has kind of a horizontal asymptote there. And the domain of this one was all real numbers. And the range was that y had to be greater than 0. So we'll remember that. For our inverse, we're going to switch x and y. So for the inverse, I'm literally going to switch x and y. So this time, when x is a fourth, I get -2. When x is a half, I get -1. When x is 1, I get 0. When x is 2, I get 1. And 4 goes to 2. Now remember, they end up being kind of mirror images of each other. So my graph is going to do something like that. Now what's neat also is x and y changed. That also means my domain and range switched. So now my domain is that all the x's have to be greater than 0, and my range is all real numbers. So that's a good point to make. So when I have a logarithm, the x has to be bigger than 0. So there's a rule about the domain. The x, or the argument, must be greater than 0. So we're going to remember that. Alright, so we just graphed log base 2 of x. Let's now graph so I'm first going to graph that log base 2 of x again. But then we're going to use that to graph a new function. Log base 2 of x minus 3. Alright, so I'm going to copy down and use that table to make the graph of log base 2 of x. And it went 1, 2, 3, 4. 1, 2, 1, 2. So I ended up doing something like this. I'm just copying what we did on the last problem. And this one had a domain of x has to be greater than 0. We have kind of a vertical asymptote here at x equals 0. Now what's going to happen for this one? What happens if I do x minus 3? Well, it's going to shift the whole graph right 3. Everything's going to move right 3. Every single little point. So 1, 2, 3. 1, 2, 3. 1, 2, 3. And guess what else is going to move? That vertical asymptote. Oh, I went the wrong way, didn't I? See what happens? I went left. It's supposed to go right. If I move everything right 3, it's going to move my vertical asymptote to here. 1, 2, 3. I got this. 1, 2, 3. 1, 2, 3. And we end up with a graph like this. Wow, I went the wrong way. That means on this graph, the domain are all the x's bigger than 3. I can only use x's that are bigger than 3. I can also think about it as the argument has to be greater than 0. So if I set x minus 3 greater than 0, I get x is greater than 3. Let's practice just that for a second, finding the domain. So, find the domain. The argument has to be greater than 0. So, the argument has to be greater than 0. The argument is this. That has to be greater than 0. Ooh, this is a tricky one. Okay. So to solve this, I would subtract the 4, then divide by -1. And what happens if I divide by -1? My symbol is going to flip. And I have my domain. Let's do another really hard one. Ooh. All right. So my argument is all of this. X minus 3 squared. And it needs to be greater than 0. Can't equal 0. It's got to be greater than 0. So let's think about that. That has a 0 at 3. It's not equal to it. If I plug in something to the left of 3, like 2. 2 minus 3 is -1 squared. This is going to be positive. Anything bigger than 3 is also going to give me a positive. And so if I want the positive sections that I'm talking about from here to here and from here to here, it's basically every point except for 3. It's -infinity to 3, but not a bracket, and then 3 to infinity. Ooh, that's a really hard one. Okay, the last thing that I want to talk about is just a couple of special logarithms. And these are so special that they get their own buttons on the calculator. They're very, very, very special. Very, very, very special. The first special one is called the common logarithm. It's base 10. So instead of writing log base 10 of 100, you will see this written as log 100. No base written means base 10. And we live in a base 10 world, so that makes sense that we kind of think of that as a common logarithm. And if you look on your calculator, right beside the 7, there's a log. And above it in blue is 10 to the x, because log is log base 10, and its inverse would be 10 to the x. So let me prove that that's log base 10. I'm going to do log of 100, which should give me 2 if it's base 10, and it does. So if I were asked to rewrite, and I was given 10 to the what some power equals 1 over 1,000, And we were going to rewrite this. This would be written as log. I don't have to write the 10 of 1 over 1,000 equals the exponent. So base 10, we don't write the base. Sort of like how square roots are used so much, we don't write the 2 anymore. There's another one called the natural logarithm. And its base is the natural number e. And we talked about that base e is used a lot in real life models. Well, when we were doing logarithms with base e, if I left it as an e, it looks funny. It looks like loge. And that's just weird. So some French guy decided to make up a symbol. But in France, they don't call it the natural logarithm. They call it logarithm naturel. So it's Ln. So Ln means base e. And it's so popular, it's on the calculator right below log. And notice that right above it in blue is e to the x, because Ln is the inverse of e to the x. Ln is log base e. So we kind of rewrote up there, so we'll do that here too. E to the x equals 54. We could rewrite that one. Instead of writing log base e, that's weird, we don't want to write it that way. So I'm going to write Ln of 54 equals the exponent.